model course, which deals with HIV/AIDS and the African continent, and she's very interested in talking to people about global understanding and engagement across international borders. And her session will be still in the same room in Kenna 306, and that's in the 12 to 1 o'clock slot. So we have one little substitution there. Cheryl was also happy to discuss pathways to including ethics and science classes, human rights, fruits of scientific process, very broad discussion, and Cheryl has been one of our outstanding model developers taking SENCER to Africa every summer. So I encourage you to look into that if you have any interest in those areas. It'll be a great session. Among the other Sunday activities that you have after the closing of the sessions, there is the hike, the tech museum, the art museum, and a bluegrass concert. There are just a few more possibilities for joining the hike. There is room for the tech museum, the art museum, the bluegrass concert, and the way you're going to get to those is that at 2:15, buses will leave the arts and sciences that will take you to those venues. Now, the tech museum and the art museum are close to the Fairmont, so you can always get back there that way. So that's for this afternoon's activities. Tomorrow, the sessions will be in the Fairmont Hotel. Now, there are some people living on campus in the villas, so we will provide shuttle buses for you to get to the Fairmont, bus you in the opposite direction, but they will pick you up at the villas. So anyone staying in the villas, anyone staying in the villas will get choose from all over, transport directly from the villas to the Fairmont, and of course back again. Now, also for the folks staying in the villas, we know that there's been a little bit of a problem with the timing of the key cards, and the university is working on that and should have it cleared up shortly. If you have any other issues or problems with that, see Amanda. See Amanda for any of your questions or problems. If you don't know what trip you're going on, if you want to change trips, if you decide you want to go on a trip, double check with her. She's ready to sign you up for anything that you're interested in and make room for you whenever possible. And today, after the morning sessions, there will be an opportunity for all of the Western Network people to get together. Those are the people that are involved in the Keck Foundation funding to develop our Western Network. They will be meeting over lunch in the Benson cafeteria, but in the pizza area, that's off to the side a little bit. And anyone who is interested in that conversation, be they from the Western area or not, are welcome to attend. So there's going to be that kind of discussion over in the pizza area for the Western Network folk and all interested. Any other questions or problems? Now that we've gotten over new business, I feel like I'm in front of my class again. Good training. So, today is day 4. We've made it quite a long way together, and it is my great pleasure to announce the participants for this morning's plenary session. But before we get to Chris and Steve, I'd like to introduce Eliza, who will talk about the models. Now, I think in the interest of time, we started a little bit late. I'll just do all the introductions. Eliza can talk, and then we can jump over to Chris and Steve. Eliza has been our model editor from before SENCER started. We have been reminiscing about the history of SENCER, and the history of the models started back in probably, like 2000, when Eliza and some of us, those early model developers from 2001, Tom Whiteley of Propellus, Amy Shacker, and myself were literally locked in the Karen's suite in a hotel in Providence, Rhode Island, and said, "Thou shalt write up your models according to these rubrics." Eliza was a very loving taskmaster, but a taskmaster just the same. And we've come to love her just the same. But she has some interesting information for all of you about how to become model developers. It's not as hard as it sounds, and we've tried to make it technologically very easy. Our next section of information moves from again, from knowing to doing. We know about your courses. We'd like to be able to do more with your courses in terms of making the models. But as we are looking at moving from knowing to doing, we still have the question about what are we doing, and is it doing anything good? Are we successful in our efforts to link science education and civic engagement? And so right from the very beginning, assessment has been a very major part of the questions that SENCER asks about itself and about its progress. And so we've been very, very lucky to have Steve and Carroll be a SENCER scholar with separate funding to create the Student Assessment of Learning Games online pre-test, post-test assessment tool that has been modified by groups of people in SENCER to be specific for this project. And it provides us with a lot of data, Steve's going to talk about all that, that actually proves for us and makes the case that we are very effective in certain areas. Steve will probably address all of that as well. And so Steve is an old friend of SENCER and has been involved almost from the very beginning. And we're really lucky to have such a fabulous tool and Steve running it, who is just a wealth of information and very happy to make all kinds of modifications for your own specific scholarship or teaching and learning interests. And then, new to SENCER this year is Chris Lazzaro, who comes to us from the College Board, and we're very excited about looking at ways to collaborate with the College Board, again, to look at assessment questions. And I'm really particularly excited about hearing how we can do that. And I would encourage all of you to think about building in assessment to everything that you do, because we really want to know that we are being effective, and it isn't anecdotal, and it isn't just our own perceptions. It is evidence-based, and we're very proud of the kinds of accomplishments we have made so far. So, Eliza, tell us about the models, and then Chris and Steve.
Hi. Every year I try to encourage the participants to consider submitting their work, not just their courses, but their SENCER work in general, as to the model series. What you will see if you go to the model website is that the models have evolved from discrete courses, because that was the early concept of the deliverable that SENCER would have, is that we would be providing these models that were heuristic. They're not meant as cookie cutter models, but examples of SENCER style or SENCER principles at work in the general curriculum around. But what you will see if you look at the model website is an evolution of this idea to course intersections, whole programs, entire general education programs at various schools. The most recent model, which just went up, is a graduate course. It's a graduate course at the University of Missouri, which is a program where they train graduate students in multiple disciplines, connect them up with a science faculty mentor to do public presentations in science. So it's a really great science literacy project. So I'm going to name the model developers that have attended this SENCER Institute, so you can see. And I'm going to ask people to stand as if you're here and I read your name off, but I'm just going to do them year by year so people can identify the model developers that are here. We have all 4 of the first-year model developers from 2001. Monica Devanis, Biomedical Issues of HIV/AIDS. Amy Schachter, Chemistry and the Environment. Tom Wood, Mysteries of Migration. Theo Koupoulis, Science, Society, and Global Catastrophes. From 2002, Trace Jordan, Energy and the Environment. Barbara Tewksbury, Geology and the Development of Modern Africa. From 2003, Joe Liticote, Brownfield Action. 2004, Kathy Middlecamp, Chemistry and Ethnicity, Uranium and American Indians. 2005, Matt Fisher, Chemistry of Daily Life. And Stephen Backelberg, Renewable Environments. From 2007, Alex Fink, The Power of Water. James Tate, Science on the Connecticut Coast. Marianne Fass, Slow Food. From 2008, Cheryl Broverman, AIDS Research, Global Understanding and Engagement. 2009, Matt Fisher, Undergraduate Biochemistry through Public Health Issues. 2010, Terry McGuire, Evolutionary Medicine. So you can see we've got a lot of the model developers have attended this institute and are available for you. Now, if you go to the model website, you will see that you no longer have to sort of contact me and send me materials in order to start the process of submitting your model. You can submit it directly on the web now through the interface, and then I will receive a notification, and then we can start the process. So explore the model page on the website. See if you would like to start entering your course data or your program data or whatever. And then if you have questions about it, you can contact me on the other end. But we encourage everybody. We'd like to see hundreds and hundreds of models up there. So thank you.
Okay, so I guess, can you hear me in the back? Amanda, can you hear me? Yeah. Okay. So I'm going to start by asking you to get out a piece of paper, or if you have a laptop, maybe draw some lines on your page. So I want you to start off by making a page that looks something like this. So draw a line down the middle of the page, about 40-60, with the 40 on the left and the 60 on the right. And draw a line across the bottom, giving yourself about 1.5 inches to 2 inches across the bottom of the page. And then across the top, I want you to put some space for, basically for topic and subject. And the reason why I'm asking you to do this is, before we even get to our goals, is because this is a method of taking notes that helps you remember them. It's based on what we now understand about how the brain works. So this is something I always start with my students, teaching them how to take notes in a way that will help them actually learn something. So the beginning part is important. Most people think it doesn't really matter what you put at the top of the page, but in fact it does. Because if you start out by thinking about, what am I doing here? What topic am I going to cover? What course am I in? You're essentially priming your brain. You're preloading information into working memory that makes it easier for you to access that information and easier for you to learn by connecting new information to that old information. So start off by saying SENCER, A4, you can do the title, or just a word or two for a topic. Then the middle part of the page. On the right-hand side of the page is the garbage section. And that's where you're going to put all your regular notes. Like whatever you do, however you take notes, I don't care. If you use outlines, if you use random doodles, if you use clusters, or if you do mind mapping, it doesn't matter. On the left-hand side of the page, on the other hand, is going to be the soundtrack bar. And what this is the secondary soundtrack in your head that's going on while you're listening to me now. Hopefully, on the right-hand side is the information that you're hearing from me, or you're going to hear as we give our session. On the left-hand side are your comments and observations, random stuff that comes into your brain, people who walk by, random bits of song that show up in your head, comments that you have, oh, this is dumb, or wow, that's a really interesting idea. All that stuff goes on the left-hand side. And the reason why it's on the left-hand side and not the right-hand side is because in our culture we read from left to right, obviously. And so your brain, your mind, your eye wants to go automatically to the left side of the page to start. So that's the most valuable strip of your page, is that left-hand margin, because that's where you want to see first. Also because there's going to be less information in this column than there is going to be in the right-hand column. So visually that's going to have priority because it's going to have higher contrast, it's going to be surrounded by a larger amount of white space, so it's going to attract your eye faster. So you're going to absorb that information more quickly than you will absorb information on the right-hand side of the page. And finally, and most importantly, the reason why this information is on the left-hand side is because this is going to act as the index of the information that's on the right-hand side of the page. The index can serve this function because it has greater emotional weight, and therefore it has a better connection to your ability to recall than the information on the right-hand side of the page. So finally, the most important thing is the bottom of the page, the summary section. And usually, you want to write a summary after about 45 minutes or so worth of information. If it's really dense, maybe half an hour. So generally, a page on both sides is about the right amount. Summary works to help you encode the information in all kinds of ways. I'm just going to mention a couple of them. Helps by putting things in your own words, helps you to review, helps you to summarize in the sense of forcing you to make decisions about what's the most important information you want to remember, what's less important, that sort of thing. But the most important function of this is the timing. So you write the summary before, obviously after the session, and before you sleep. This is important because sleep acts primarily as an erasing function in relationship to memory. So it's very important that you do this before you sleep and lose that information. For best results, then, you review within 24 hours of this lecture after you've slept, because that helps you move information from working memory into long-term memory. So it helps you encode the information for maximum recall later. So this is a very powerful method of taking notes. It works very effectively. I urge you to try it today. If nothing else, then later this afternoon, before you sleep, write your summaries. How many of you go to a conference like this, take notes vigorously all day long, feel very inspired, think, oh, I could use that in my course, I could do all these things, and then you get back home and you get buried in a daily email, and these notes go in the file folder somewhere, and all those good plans kind of slowly fade away. So, having some notes that are compressed and that are easy for you to remember will help you combat that phenomenon. So that will be your motivation later on today for making your sermons. So, goals. What are our goals for today's session? And we're trying to model the behavior that we're going to talk about today. So, starting with the big picture goals. We're trying to move you from wherever you are today, and hopefully you're a little bit further along this path than you were when you started coming to SENCER, away from the learning as acquisition of facts and teaching as the Sherwin-Williams model, covered the earth, to more defining learning as facilitating enduring understandings, durable learning, habit formation, and teaching as developing and mentoring self-directed learners. So, very big picture goals. More specifically, to give you and motivate you to use some tools that you can use to revise and align these 4 elements of course assessment we're going to talk about today. Epistemology, course goals, course pedagogies, and the assessments that you use to evaluate your students' progress towards the goals that you've set, and the way that your pedagogy affects those goals. More specific still, we're going to help prepare you for the coming changes in the AP Science tests, and the effects that those changes will have on your students and on their abilities and expectations as they enter your classrooms.
So, what is our problem statement? Our problem statement is really the overall need that drives our purpose. So today what I'm going to be discussing is the redesigned advanced placement biology program. And to kind of start to talk about, first of all, why did we decide to make the changes that we made? And how will the changes affect students that are going to be entering into your classrooms? So Jay and others have made a comment about this report, the 2002 NRC report, that really pushed on AP, excuse me, really pushed on AP to make some changes. It pointed out a couple of really important things that we were doing with our old course that were not necessarily preparing students in the right way for your courses once they got to the college level. The first and foremost was this idea of the mile-wide, inch-deep problem that AP courses were covering all the content you can possibly think of. That's the Sherwin-Williams model that we just heard about, without getting very deep at all. And it was emphasizing, it was kind of de-emphasizing really the inquiry skills and the processes in lieu of covering as much content as possible. So, what did we do? Advanced Placement, College Board, went out and they looked at university courses and they said, how is our program helping prepare students for your courses? And what we found was actually we were doing all the things that Jay's report was saying, that we were amplifying this idea of the mile wide, inch deep. We were not really getting to the scientific reasoning. We were really teaching kids how to memorize lots of facts. And really, for me at least, the most important part is this last one, that we were perpetuating this idea or this perception that students, that science is a finished body of knowledge based on rules rather than reasoning. So now we have to decide, how are we going to make those changes? And so Stephen's going to come back up, talk about a couple of things, and then I'll get back into what exactly we were trying to do with AP.
So let's start with epistemology. And because, as I'm going to show in a minute, how you think about learning and knowledge deeply affects the way that you teach, and more so than what you say about how you teach. So I want you to take 2 or 3 minutes and write an answer to this top question. What is learning? And the 2 questions below it are heuristics. So if the big question is too big for you or too abstract for you, think about what does learning mean to you? How do you know when you've learned something? So 3 minutes, go. If we had clickers, I would ask you to vote, but we don't, and I'm not going to use the table counting method because I don't want to out people too early. But what I'm going to do instead is go through some general categories that people's answers can fall into, and I'm going to talk a little bit about the relative proportions of those answers. I've given this assignment to lots and lots of groups over the last couple of years, everything from college freshmen to seniors to faculty developers. And interestingly, the relative proportions of answers are remarkably stable over all those groups. The most common set of answers revolves around understanding. And so those are some typical answers that fall into that category. This is generally 40 to 50% of the overall response, and often even sometimes up to 55%. So this is by far the most common set of answers. The next most common set of answers has to do with skill development. And this is usually in the 30 to 40% range. And those of you who are thinking ahead, or thinking backwards, I guess, to Jay's talk yesterday, will recognize that both of these correspond to the lower levels of Bloom's taxonomy, cognitive taxonomy anyways. And so these generally are the kinds of skills that we expect students to develop in high school and to surpass in college. The next most common set of answers is a significant step down. This is usually in the 10 to 15% range, occasionally as high as 20%. Affective change has a lot to do with durability of learning because it provides motivation and it provides a lot of the neurochemical basis for learning to like something, becoming engaged in things that makes that learning rewarding and prompts you to continue doing it so that it continues to last in your life. The last category, and by far the least represented, usually in the 5% range, is habit formation. And yet I would argue that for almost all of you, the ultimate goal that you have in teaching your students has to do with making long-term, relatively durable changes in their behavior based on the experience that they have in your class. You want them to change in some way that will last beyond the final exam. And so I would argue to you that at some level you have to deal with this question of habit formation. So part of the epistemological point that I want to make is that the kinds of learning we're talking about doing in SENCER have to do with changing attitudes and habits, because those are the kinds of things that lead to long-term change. And how we, as teachers, think about what learning means, of course, affects how we teach. And so I would again take us back to Jay's slide here. So I would urge you to try this experiment at home, but only in a moment when you are feeling particularly smug or strong. So I would ask you to put your course learning objectives up against Bloom's taxonomy and to just sort of see where they fit. So what's the average level at which your course objectives correlate with what Bloom says here? And by the way, there's a reversal. A newer model of Bloom has an additional layer on top which says create. And you can actually just Google Bloom's taxonomy under images and you will see a couple of variations of that. So rank your course, and then ask your students to use a list of verbs, and I'm not going to spend any time here, but I want to point your attention to these lists of verbs. And so these verbs are the assessments that you use. What kinds of verbs do the assessments that you use tend to use most? One thing I can tell you, having done this a number of times with a number of different people, students get this really fast. So they will be able to tell you very, very quickly what level of Bloom's taxonomy your course actually tests them on. So these are, of course, the lower level skills. These are the higher level cognitive tasks. But go ask your students. See what they say. So we've been at this about 20 minutes now, and brain research says that most people can't really concentrate on anything, even if they're trying their hardest for more than 20 minutes. So I'm going to follow my practice and ask you to get up for a minute. We're going to shift gears for a second to help you refocus. So what we're going to do here is called cross-lateral activity. The easy form is simply give yourself a big hug. And if you do that, I want you to focus on what's happening on your hands as they touch the opposite sides of your body. Okay? Those of you who are feeling more adventurous can, of course, do the pat the head, rub the tummy thing. And then, of course, you want to reverse that. Pat the head, rub the tummy. Those of you will find it's easier in one direction. Those of you who are feeling really advanced can try the punch spot. Or Charleston, where you're the common ingredient here is simply the fact that you are reaching from one side of the body across the other side of the body. And the reason why that's important is because it opens up the corpus callosum. And when you are engaged in one kind of activity for a long period of time, say an intellectual activity like taking notes or trying to learn something, you tend to load up one side of the brain. If you're doing something artistic, it will be the other side. But opening up the corpus callosum essentially helps the brain load balance. And so by engaging the other part of your brain, you become more efficient at processing, you learn faster and easier. So one of the things I do with my classes is every 20 minutes or so, we have a little activity that helps them open up their brain a little bit, and I have them go out and sit on a tree, because sensory response helps you open up multiple channels of learning. So every 20 minutes, a little something, change the pace. Go ahead and sit back down, please, and we will move ahead. And you're up here.
Okay, so we started to set up our learning theory here a bit, but how does any of this actually relate to AP, and what is it that we did? Well, this slide is titled, What's the Big Idea? And the idea behind the big idea is, our first task when we decided that we wanted to redesign our courses is we gathered a group of experts, and we sent them out and we said, look, forget the entire content of the course right now. What I want you to do is I want you to think of what are the big ideas, the organizing principles of the discipline. And today I'm just going to be talking about biology, so I'll just keep all my examples there for now. Around biology, and then come back to us and let's talk about them. So we sent them out for about a month or so, and they went out and they thought about this and kind of rolled it over and brought it back, and they came up with about 10 or 12 different big ideas. And so we thought about it, and we read through them, and we said, these can't be big. We can't have 10 or 12 big ideas for one course in biology. That's just, it's not possible. So we sent them back out one more time, and they came back, and they had only 4. We tried to limit them to 5, and they did a really good job, and they came back with just 4. The idea behind these big ideas is that they are the key concepts that the entire course can hang on. All of the content should be able to fit in one of these 4 buckets. So then we took the content of the course, and we looked at it again, and we said, all right, well, where does everything go? And we found that there's a lot of the content of the course didn't fit underneath one of these 4 big buckets. So we decided, okay, well, that's probably where we should start cutting. That's probably the first thing we should start to cut. And Martin mentioned this in our session the other day, but actually we cut a whole bunch of this, and we actually hit pause at that moment, and we said, well, I don't know that we should keep going here. We should go and talk to a few colleges and universities and decide if we've gone too far by just taking out this initial bit of content. And we brought it to them, and they read through it, and what they said was, you can cut more. This is just fine. Keep going. So we were happy with that. We went back to our content experts, and we said, all right, what are the enduring understandings underneath each one of these big ideas? In other words, what is it that we really want students to know and take away from the course? And limit that to only 4 or 5. And then the last piece of all of this is the science practices. And this gets back to the epistemology stuff that we were just talking about. These science practices actually cover every domain in science for AP, so they don't change. The content, the big ideas and the enduring understandings change whether you're looking at biology, physics, or chemistry, or AP environmental. But the practices do not. They are kind of the connective tissue between each one of the disciplines, and they set up what does it actually mean to be doing science. So these are our 3 key components. Yeah, go ahead. Good question. Hold it for just 1 second. I think I have a slide that might help that in just a second. So these are our 3 main components of the new course: the big ideas, the enduring understandings, and the science practices. Here are the 4 big ideas, and I hate reading from slides, but I feel like this is very important, so I'm going to just do it for this one slide. Evolution. The process of evolution drives the diversity and unity of life. 2, cellular processes and energy and communication. Biological systems utilize free energy and molecular building blocks to grow, to reproduce, and to maintain dynamic homeostasis. 3, living systems store, retrieve, transmit, and respond to information essential to life's process. And big idea 4, interactions. Biological systems interact, and these systems and their interactions possess complex properties. Everything in our new course falls underneath one of these 4 pieces. If it's not in the course. Okay, so a minute ago I had a question about the enduring understandings. What do we mean by an enduring understanding? Well, what we want for a student, or what we mean by that kind of that durable knowledge, that takeaway message, is we want it to be something that a student will remember 50 years from now. So we hear about the citric acid cycle as being something that was in the old course. Well, it's not really in the new course the same way, because no one remembers it. I mean, I was a physics person, so I certainly don't remember. I'm sure there's some people out there that actually teach biology that may remember parts of it. But trust me, your students don't remember it after they take the test. So here is that very first big idea under evolution, and these are the 4 enduring understandings. This is what we're trying to target with the new assessment. So the change in genetic makeup of a population over time is evolution. Organisms are linked by lines of descent from common ancestry. Life continues to evolve within a changing environment, and the origin of living systems is explained by natural processes. So the idea here is, if in 50 years an AP student who is now possibly not a biologist at this point remembers these 4 things, we feel like we've contributed greatly to the knowledge of that student and have also prepared them for your course, your biology course that will be coming afterwards. So I'm going to stop here. We're going to get a little bit more into the learning theory with Stephen, and then we'll get back to how we actually try to assess a few of these things.
So I want to start with just an overview here that however you want to define learning, there's all kinds of different ways of defining learning, depending on your discipline and how deep you've gone into it, but all of them have a common core of functions. That a person has to acquire something new, they have to be able to retain what they have acquired, and they have to be able to transfer it into a new situation. So I want to dive a little bit more deeply into those things. We're still sort of fleshing out epistemology, and we're going to use this epistemology to help us generate course goals. So A is for acquisition. So how do you acquire things? And the mnemonic that I teach my students is actively build connections. And the reason for that is we're going to dive a little bit into the way the brain works. So learning is actually making connections. And these are neurons here, as you see. And so as neurons grow, they connect to each other. And I want to make one small point here as we go along. I want to point out these Schwann cells up here, which create the myelin sheath, which acts as an accelerator of neural signaling. And the reason why this is important is because those of you who are teaching traditional students are dealing with students who are in the process of developing those Schwann cells and the myelin sheaths during the time that they are in your classroom. What that means for you is that there are radical differences in the speed at which different students process information. Doesn't mean they're stupid. It just means that they process information more slowly than other people around them, depending upon how fat their sausages are, right? So, nothing that you can do changes the growth of their sausages, but knowing that often helps people become a little bit more patient with people who they otherwise are tempted to label as dumb or a little bit slower than the other people. Well, in fact, they are slower. It's not their fault, and they'll get faster soon. So don't give up on them yet. Neurons that fire together wire together. This is a picture of 2 pyramidal neurons firing at the same time and starting to form a synapse between them. Looks like a very nice little dance that they're doing. Learning is making those connections. So when you talk about the Foresters only connect, it applies all the way down. It's not just a metaphorical concept. Learning is making connections all the way down to the neural level. Ideas and meanings are patterns of neural firing. So having a set of neurons fire in a certain order, in a certain space, is that idea. That is how it becomes represented to you. How does this help us? It helps us by reminding us that the primary thing that we're doing is not dispensing information. There's a fantastic quote I have from Scientific American in July of 2010. Nothing we can learn stands in isolation. We can sustain new learning only to the degree we can relate it to what we already know. So learning itself has the structure of an analogy, right? Using models, mnemonic devices, analogies and metaphors are the ways in which we build actual learning as opposed to simply distributing facts to people. Those facts can't last because they're not connected to anything. And you're leaving the hard part of learning to the student by saying, oh, it's up to you to figure out how it connects to stuff, right? If you can help them get in the habit of learning to connect what they are supposedly learning to the things that they already know, show them how that's done, teach them that that is how learning works, then they'll be a lot farther ahead in the game and more equipped to do it on their own once they leave your classroom. The other thing that we know is that learning physically changes the brain. Not only do the synapses form as a result of the experiences that people have, but the brain itself physically changes size. When you learn something new, especially something difficult, the region of your brain that is doing the most learning grows physically by up to 2.5%. And obviously, this can't continue very long, otherwise your skull would be a serious impediment to further learning, right? So how does this work? How come our skulls don't just explode? Well, what happens is that that region of the brain does expand, but then once the learning starts to slow down, it shrinks back again. But when it shrinks back, it has to do something with all that mass. So what happens is your brain becomes more folded. So you have more coruscations as the brain shrinks back to size. That increases your processing power. So learning helps make it easier to learn. So the more you learn, the easier it is to learn. And not just because there's more stuff for you to make connections to, but because your brain adapts physically to the learning process and becomes better at it. The other thing we know about learning in relationship to acquisition is learning hard stuff helps your brain grow. We used to think we knew that people didn't get any new brain cells, that you were just born with whatever you had, and depending upon how much you drank or what kind of drugs you did in college, you end up at the result with more or fewer, right? And you sort of had to pay your money to take your chances. But we now know that that's not true. You actually do get new brain cells, mostly starting in the hippocampus. But there's a trick, and that is that you only get to keep them if you work them. If you don't work them right away, they die. And the harder stuff that you're learning, the more you get to keep. So the couch potato loses those brain cells, and they're post-college right here, right? But people who continue learning actually replenish their brain as they go along. And here we can see some of the effects of that. The couch potato neuron over here is one that doesn't practice learning a lot, and so, as you see, winds up with an impoverished neuron. And the one who spends time learning new material is over here. Obviously, this neuron has a lot of connections and is in a position to make a lot more of those connections. So in my class, we talked about our class mantra as fat sausages, foldy loaves, and hairy neurons. These are some goals that we're seeking. And when I suggested that we should put these on a t-shirt for my learning facilitators, the boys were okay with it, but the girls rebelled. So you can't have that on your shirt. They did not want to be fat, foldy, and hairy. So some key factors that I want to pull out of this. Learning is making connections, and it has the structure of an analogy. We also know that it only happens when your brain is active, when you are paying attention, and that effect is ramified by being intentional. If you are trying to learn something and you are focused on doing that and you have some skills with doing it, you do it better, unsurprisingly. So the whole movement towards active learning is actually beside the point. Learning is always active. It only happens under those circumstances. We also know that positive engagement, motivation, all kinds of positive emotions help people learn because they help you encode and remember information. So I'm making a momentary shameless plug here for what I call meta-learning, which is the fact that if you teach your students how to learn, they will get better at it. Our students actually really don't know much about how learning works, and so their habits that they've evolved around learning are mostly random and mostly not very effective, and that lack of effectiveness is often discouraging to them, which puts them on the downward cycle. Teaching them some things about how to learn helps them get better at it, helps them succeed more quickly, and it creates a positively reinforcing feedback loop. There's more information about this on a website that we recently put up called Learning Habits at WordPress.com, and there's a lot of resources on how to set up these kinds of activities there. So once we've acquired something, some new piece of information or some skill or some attitude or hopefully a habit of some kind, you have to retain it. So these are some common ways of thinking about how you can retain information. So the review that we talked about, that's the summary that I'm asking you to write. Being able to explain to other people, testing yourself or testing other people to make sure that they know, so this sort of mutual testing back and forth, being able to analyze something, and of course being able to integrate what you have learned with what you already know. This is how retention works. This is a picture of a synapse. I'm not going to talk about this very much here, except to point out that there's this lovely little gap in here. So synapses, when they form, the neurons don't actually physically touch each other. There's a small gap across which electricity has to flow to maintain that synapse. And there's obviously a lot of stuff happening in chemical soup in between them that can aid or hinder that communication. So this is one of the ways in which things like stress, positive emotion or negative emotion affect how you learn. So apathy, for example, blocks it completely. Really very, very high stress levels do the same for most people. Moderately high stress levels, on the other hand, which we call eustress, help you remember more. So we have to sort of work our way into the middle here. But the most important thing that helps you maintain a neural connection is practice, right? The more that this neural connection fires, the easier it is for it to fire. So the most important thing that we need to help our students learn is practice. So key factors shaping retention. Strong emotions, right? You want to be in the middle range, as I was saying to a group the other day. Most people have very strong memories of their first kiss because it's such a nice, lovely experience. They've been looking forward to it a long time, and generally happens sort of in the moment, so there's not too much trauma involved. On the other hand, most people have a much harder time remembering their wedding day because the stress levels are so much higher there, it prevents certain kinds of encoding. So the wedding day tends to be a little bit fuzzy, but the first kiss, boy, that thing stands out. So that shows you how different levels of stress affect your ability to encode things. Everyone wants to remember their wedding day. Now we wind up keeping it on video so we can actually remember it. Repetition and reinforcement. The most important key to retention. Sleep we talked about a little bit. Sleep acts primarily as an eraser. It weeds out the information that's not important from the day and sorts and files the information that's the most important. So sleep and then review. Exercise is one of the strongest effectors of retention. There's a wonderful article in John Beatty's newest book, an experiment that they did with 8th graders showing that if you have 45 minutes of exercise at the beginning of the day, their academic performance increased so much, it was unbelievable. I would advise you to check it out. Hydration. If you are even moderately dehydrated, your IQ drops by as much as 20%. So simply knowing, for students to know that when you come to class you need to be hydrated, helps them enormously. Multi-modal learning environments are better than single mode. So environments that are rich in sounds and smells and those kinds of things help people remember information better than environments that are sterile. Lastly, transfer. And I don't have a mnemonic here. My mnemonic actually has to do with bus transfers or job transfers. So why do you take, if you're taking a bus, why do you get a bus transfer? Because the bus that you're on doesn't go where you want to get to, right? So in the same way that you learn a new mathematical procedure, being able to apply it to the same piece of information over and over and over again doesn't help you. So you need to be able to apply it to new kinds of contexts. Same thing with a job. You change jobs because the job that you're in isn't getting you where you want to go. So you need a new job. Transfer is taking what you know and applying it to something that you don't know. And it depends largely on pattern recognition. So if you look at, in the book, How People Learn, the Ransford book, one of the big differences that they found between novice learners and expert learners is experts recognize patterns more quickly and use them more effectively. So one of the things that we need to teach our students to do is how to recognize patterns. Also changing set. How you change set to look at things from a different perspective helps you transfer what you know from one setting to another. As Bransford also teaches us, it is the most difficult part of learning by far. And therefore, should be the most practiced, but in fact the least. So if you want people to be able to use what you've taught them in your lecture or in your discussion section in a new environment, you have to teach them how to do that. Because generally speaking, people are terrible at this. So they need to practice as much as possible. Some quick principles derived from neurobiology. I'm not going to read this list, as this slide deck will be up on the web. You can access it later. This is mostly repetition of what we've just talked about. So at this point, I'm going to turn it back over to Chris.
So we've talked a bit about the learning theory, and now we're going to look at, if you remember a little while ago when I last spoke, I showed 3 bubbles, and one was the big ideas, one was the enduring understandings, and the last was the science practice. So I started with the big ideas and then moved into the enduring understandings, and here are the science practices. Now I won't read all of these, but again, these are the science practices that are the connective tissue between all of the science courses. It really sets up the epistemology of what we think all AP students need to know in order to be prepared for any science course. And so it's things like using models and representations, using mathematics, engaging in scientific questioning, data analysis, constructing scientific questions, and then that very last one, which I think is kind of like the highest level, is being able to connect and relate knowledge across various scales, concepts, and representations across domains. So I've learned something about evolution in biology. How can I apply that to what I'm learning over here in chemistry? All right, so how do we actually measure some of this stuff? Now, for those of you that have actually gone through the process of evidence-centered design, I'm going to apologize now because I really oversimplify it. But I'm doing it to illustrate a point. And so what we've done in the AP Biology courses, we took the big ideas, we took those enduring understandings, and we took the science practices. And this is kind of like Jay's, and then a miracle occurs, right? So it goes through this, we throw them in a hopper, and something happens. And we created claims. And so what we tried to do for all of the content framework that we had, and all of the science practice framework that we had, was intertwine the two of them and say, what claims can we create? What do we want the students to know? And all of the claims actually start. The student can. The student can understand something, the student can do something, the student will use data to whatever. And I'll show you a couple examples of this in just a second. So this is what we call evidence-centered design. And again, I'm oversimplifying it to illustrate a point here, which hopefully will become more clear in just a second. But it's what is the evidence that we kind of get to the claim that we're laying out, and then what task? So we have a claim, we have an evidence, and we have a task. The claim is what you just saw. It states the essential knowledge that you want a student to have. The evidence is the acceptable evidence that you as the teacher will accept that they understand the claim that you've laid out. And then the task is, what are you going to have them do to show you that evidence? It could be as simple as a test question. It could be a homework. It could be a project. It could be a lab. It could be collaborative work. It could be almost anything. That is the task. What you're looking for is the evidence. So I'm going to pause there for just a second. I'm going to show you, because I know I'll get 100 questions on this if I don't do this, the redesigned schedule. So the bio course begins this year in 2012-2013. So in September will be the first crop of students entering into the new biology course. The exam will be given in the spring of 2013. Chemistry will roll out after that. We've officially announced the release of this, and it will start 2013-2014. And then in 2014-2015, we will roll out physics and environmental science, and we may actually break those two up, and one might be afterwards. We're not exactly sure just yet, but it will be pretty much around that time frame. Okay, so what does the actual biology exam look like? That's the one that we've released. That's the one that's starting. I can talk about this one a little bit more. So section 1 contains 63 multiple choice questions, 6 grid-in questions, and you get about 90 minutes to complete all of that. Grid-in questions are, we have like the bubble sheet where the color codes, so we do everything in bubble sheets, and the student will calculate an answer and get something like 52.7, and the grid-in is actually, they would grid in the 5, the 2, the point, and the 7 as their actual answer. They get 90 minutes to do that, and it's 50% of the exam weight. Section 2 is going to consist of 8 free response response questions. 6 are short, 2 are long. I'll show you examples of those so you can understand the difference between the two of them. And again, they have 90 minutes total to complete this, and it's 50% of the exam weight. We field tested all of this. We expect that just about every single student will have no problem completing it in the time that we've laid out. We've even calculated about 10 minutes in section 2 for the reading time that's required. And if students have a disability that requires them, it takes them longer to read through the problems, they can apply for extended time and everything. Okay, so what's the difference? Let's look at a few of the old versus new questions, and then I'm going to deconstruct them so you can actually see those little bubbles that I have just shown you, and we throw them in the hopper and we can actually see the claim and the evidence. So here is an old question, and I'm not going to read this to you, so just take a second to look at it. And it doesn't make a difference if you don't have a biology background. As you read through this question, you should be able to note that it's relatively low level, and what we're actually testing here is memorization. So whether or not you know something from biology, it might help you, but if you've memorized this particular diagram from the book and you remember the professor or teacher talking about it, you might be able to come up with the correct answer. And so in case you're playing along, I have the answers. It's the last one. Here's a new one. So the idea here is that even if you did have the book, right, it's not necessarily going to be clear what the answer is. It requires a much deeper level of thinking about what actually has to happen. The diagram itself actually relates to the question in a way that makes you have to look at it and use it in some way. And here's the actual answer, again, if you're playing along. So let's take a second to just deconstruct this question. So it's big idea 2. Biological systems utilize free energy and molecular building blocks to grow, to reproduce, and to maintain dynamic homeostasis. It also consists of science practice 1.4. Don't worry about the coding, but if you have seen any of this before, or if you go on our website, you can actually download it so you can find all of the science practices, big ideas, and enduring understandings. So I'm throwing the code up there just so you can see it. The student can use representations and models to analyze situations or solve problems qualitatively and quantitatively. And then the enduring understanding. Organisms use feedback mechanisms to regulate growth, reproduction, and to maintain dynamic homeostasis. Now, we didn't just write the question from here. We first had to create the claim. So again, to oversimplify the process, these all go into the hopper and they get mixed up, and we come up with a claim. The claim for this particular question is, and this is an example, I can't actually release and show all of you, I wish I could, all of the claims and evidence statements. So this is a summary, of what it actually is, but it's close enough that the students can analyze biological processes involved in growth, reproduction, and dynamic homeostasis that include temporal regulation and coordination. Right, that's still not good enough to actually create the question. So we have the claim. This is what we want the student to be able to do. Here's the evidence now that gets to that claim. Now, you're probably sitting there and thinking, I could have come up with something better by combining those 3 little bubbles and come up with a better claim. I certainly could have come up with better evidence. It's not to say that there's only one claim that you can create from that combination, and there's certainly a lot of evidence that you can create. These are just examples, and as long as it was true to those combinations that we created, we felt as though it was good enough for what we were trying to assess. All right, here's another one, and again, these are all biology questions, but this one's a little bit closer to chemistry, so hopefully it'll be more relevant to some of you. old questions. This is not one of the new ones. Anyone want to venture an answer before? Very good. Okay. Again, here's one of the new ones. Well done. That's 2 points. So again, you can see that the question is a bit more complex in what it's asking, but it's not necessarily more difficult. It's more, it requires more knowledge. It requires more knowledge of the discipline. So let's again deconstruct this for just a second, and then we're going to stop and have you guys do something around this. So it just happens to be that it's big idea 2, again. This time we're looking at science practice 4.1. Students can justify the selection of the kind of data needed to answer a particular scientific question. So this is about the justification of different types of data sets. Organisms use feedback mechanisms to regulate growth and reproduction and to maintain dynamic homeostasis. They go into the hopper and create the clone. So at this point, what we would like to do is we would like to have you guys discuss the rest of this, right? What is some of the evidence that you might be able to come up with that would meet this claim? And then if you get to that point relatively quickly, what would be some of the tasks, right? So the tasks that we've been looking at here are just simply, it's a question, right? It's an exam question. That is the task. The evidence is that they can choose the right answer, but from the evidence statement that we're going to construct. You might be able to come up with a different task, like, actually, I think I would get at this better by doing it through a lab. Or, I have a really good homework question that I asked that relates perfectly to this, and this is what it is. So take 5 minutes, discuss it amongst yourselves, and if you're sitting in a group of just physicists or something, you might want to break up and sit elsewhere. But we'll give you 5 minutes to start.
But
So, just given the limited amount of time we have, I'd like to just try to pull everybody back together, and if we can get one group to share one piece of evidence that they came up with, and then maybe another group to share one task that they came up with, we're going to transition into our last thing that we want to do with you, and then wrap it up. So, do I have any volunteers that would like to share one bit of evidence that they've come up with for this claim? Anyone? Okay. So the actual evidence statement that we have for this particular question is here. And again, as you can see, there's a lot of places that you can go once you've created that claim. Now, obviously, we were looking for evidence that would help us create an assessment framework. That was kind of our task. And so that's why this evidence is kind of pointing in that direction. But I think the two examples that we have were pretty right on. So we're going to skip down in the interest of time. There were just a couple more examples, and if anybody would like to see them, they'll be in the slide deck. There's an example of a short free response and a long free response, both broken down appropriately with looking at the old type of a question, the new type of a question, and then the breakdown. Okay, so I kind of ruined the picture a little bit because you got to see it before. Do you want me to start this? Or? Okay, so the very last thing that we were thinking about, and we're probably not going to have enough time to have everybody do this, but we're going to tell you about it, and then this is kind of our plug for our next session. If you want to come, we can go a lot deeper into all of this. Is that, remember I was telling you that we first kind of set out by convening a group of consultants, and we said we need to come up with these big ideas. What are these big ideas that organize all of the content of an AP biology course so that we can hang all the content on it, figure out what doesn't fit, decide what the enduring understandings are, and create an assessment framework. Well, what we quickly realized when they came back the first time with those 10 or 12 is that the big idea itself is really just the tip of the iceberg. And there's a whole lot of questions that you have to ask to just be able to get to the big idea, which is the very first step of all of this. So if we remove the first half of the iceberg, we come up with a few, yeah, you're loving all of mine. We come up with a few questions. So here are the questions. I'm just going to put them up quickly because I don't have a lot of time to read through all of them. But we found that these questions here were the questions that we needed to ask before we could get to the big idea. And we had to have this whole process in mind before we could start. So we really had to understand kind of all of the components. What would the science practices be? How would those come together to create these claims? What will the claims look like? They'll be student-centered. What grain size are we aiming for? Once we get past that, what is the type of evidence that would be acceptable for one of these claims from an AP student? That really kind of sets the gauge or the achievement level that we're looking for. And then what tasks do we want? For us, being at the College Board, the task question was a little bit easier because it was just, write test questions and have them answer them. But to help our teachers, it really becomes, well, what labs are they looking for around this kind of stuff? How do you teach this content? What's the instructional method and sequence to all of this stuff? So these were all of the questions that we had to be able to ask before we could get to the tip of the iceberg, which was the big idea. So this is what we plan to talk about, I think, a bit more in our next session, and we'll go much deeper there. I'm going to end here, and if Stephen has anything else to say, but thank you very much.
So I want to expand beyond the big idea and to sort of review a little bit about what we've done today and to sort of recontextualize that. So what I hope we've done is walked you through a way of seeing a learning experience as vertically integrated, and that what you are designing in your courses and in your curricula should reflect that kind of vertical integration. So we started with epistemology. We started with how do you define learning? What does it mean to learn something? And how can you tell when somebody has learned something? We went from that into course goals. What are you trying to get to? And so hopefully this could have to do something with enduring understandings. Those enduring understandings revolve around these big ideas, and they help integrate the big ideas with the actual practices that you are trying to encourage. So these three spheres are in fact not individually isolable, but they interact in very complex ways. And so, as Chris said earlier, and then a miracle occurs and they spin out of the hopper. I want to suggest here that the miracle is you. That you are the ones that make this happen. And that as a result of that integration, you come out with those questions, those assessments, those tasks that help you prove to yourself, to your students, and to others that the learning is really working. Thank you.
Thank you again. It was a fabulous model of a duet. Give and take. It's all about how SENCER is collaborative, if nothing else. And we have some great models here. I can tell you that my brain hurts. I'm feeling very fat, full, and hairy. And proud of it. But thanks again to our speakers this morning and for you all coming out. We're about to break up into our next series of breakout sessions. But before we do that, we have one more very serious announcement to make. And that is that we are very privileged to have both of our co-directors almost always share their birthdays with us. Yesterday was David's birthday, and today is Karen Oates' birthday. So take every opportunity to take that. So happy birthday, Karen. Thanks so much, and enjoy the rest of the sessions of the day.
general science. Okay, so we'd like to get started. So I think before we start kind of running through what we want to talk about, what we'd like to first do is get everybody seated in some sort of organized way by discipline. And so if you are biology or consider yourselves to be biological sciences, why don't you sit at the table where J is? Yeah. Yeah, there you go, right. If you are physical science or physics, come sit here, and if we have enough to break that out into chemistry and physics, sit at two different tables. I don't know that we'll have enough for environmental science and everything else, so for now, why don't we have a miscellaneous or the all other science group? Yeah, how about right here, around this table, and if you find that there's enough of you that you want to break out into different groups, that's fine. Yeah, can we put the math people probably with the physics people just to start? If that's okay with you. Sorry. So, I think they just didn't want to associate with Jay, and that's why they sat at this table. Okay, so what we'd like to do is we're going to spend most of the time here having you do some work. We don't want to be here kind of lecturing you the whole time, but what we do want to do, and the reason why we've kind of sat you in these different groups, is we want you to begin to think about the content of your own courses and how you might organize those, first starting with those big ideas, then kind of breaking those big ideas down into the enduring understandings. And the ultimate purpose for this is what we'd like to try to get to is the tasks at the end of those evidence statements. So what are the tasks that you would do in your classrooms that you would elicit the evidence of these enduring understandings? Now you might immediately start off by saying, all right, well, this is no problem. I've got a whole bunch of tasks that I do in my classroom, and I'm sure that they all relate back to enduring understandings, so here they are. But I really would like to try to push you to do this in this somewhat organized way that we've tried to present here, so that you can actually point to, well, I have, and you can't come up with more than, we'll limit it to 5 big ideas. Even that's probably too much. You know? So let's say 4, but you get 1 extra one if you just can't live without the 5th one. And then, no more than 4 enduring understandings. And if you want to just pick one strand, like get one really good big idea, and then 1 set of enduring understandings, I think that would be just fine. That would be too much for us to work through anyway in the hours that we have. And so that's where I think we should start. The one small issue we will have is the science practice component. And so what I'm going to suggest, I'll leave the science practices up here in just a minute, is that you use our science practices, unless you just can't live with them. But it's the epistemology of science, so it shouldn't be too far outside of the realm of possibility for your classes. The math group, because it would be a different epistemology, you're going to have your own set of practices. You'll just have to kind of think of those yourself as you come up with those claims and evidence statements. But again, they shouldn't be too different from what we have. And so, rather than kind of representing any of this. I guess what I'd like to do is just start by asking a few questions. Does everybody understand what we mean by a big idea? Does it make sense, kind of the big ideas that I put up for biology, and do you see how that would kind of be the organizing principles for biology, and how you might make that work for, let's say, physics or chemistry or any of the other groups? So I think it brings up two important points here. One is that the big ideas have to relate back to the level that you're aiming for. And so if that's like a middle school student, the set of big ideas for a biology class in middle school is definitely going to look different than the set of big ideas for the university course. At least I feel that would be the case. And the reason for that is what you're trying to do is you're trying to prepare them for whatever it is they're going to be getting to. And so you don't want to be saying the organizational principles of middle school biology are sequencing of the genome or something. But what you want to do is you want to kind of set the stage for that. The second thing is that these big ideas should not be static, right? I think the idea that these can change over 10 years would be appropriate, right? And, I know I'm going to get this quote wrong, but Bruce Alberts talks about how all of the knowledge in math we've known for the past 70 or for the past 100 years or something like that, but all of the knowledge that we know in science has come up within the past 50 years. I know I butchered that, but correct me. So anyway, so that's kind of what I would say about this, but so really try to make those big ideas relevant to your course, where the group of students that you're teaching and the course that you're teaching.
I understand what you desire to do by having a small caption of the big ideas. Isn't the text below the goal, isn't that really the big idea?
It is, yeah, it absolutely is. In fact, if you go onto our website and you download the content framework, you'll actually find that we have the big idea, we have the bold word, we have this one sentence, and we have about 3 pages explaining what that one sentence actually means.
The one sentence is the thing you really want.
That's exactly right. If you can boil this down to that one sentence and it captures in your head that next 3 pages of what you mean by that, and you can pass it off to someone else and they can understand it, which is what I hope you can glean from all of this, then that would be considered the big idea. Jeff.
I just want to come back to the Thomas thing, because things like genomics, for example, to me would fit under big idea 3. So that is a huge idea that's much more conceptual than the kinds of things that we do typically in biology classes in metabolism, photosynthesis, yada, yada, yada. And so it would seem to me that you could really enhance students' understanding of big ideas by sort of bringing them to the forefront of what's happening by the genomic revolution. And you could also use the genomic revolution to bring them to the forefront of evolution, because genomics is now reinforcing and extending the kinds of stuff that we traditionally learned from a lot of different other areas, including molecular biology. Genomics just brings it to a new order of magnitude in many ways. So the cutting edge stuff, I think, really can be folded in and used to extend these things.
Yeah, I think that's really relevant. All of you were talking about doing information technologies.
Yeah, absolutely.
But you're talking about the term you use for number of bytes of information.
Yeah.
Whereas that computer lines, whatever, are revolutionizing today at a more rapid rate than the past tradition or second tradition. So how are we dealing with that concept? The importance of it with regard to us as college teachers is very
also with some of the work that Martin and Achieve is currently doing with the Next Generation Science Standards, which will hopefully begin to kind of triangulate and give you a sense of, this is what you can expect out of the student, that you'll be getting in 10 years or so.
Comment about the big ideas and the use of the iceberg I thought was really interesting. However, when you look at your picture that you got, it's scientifically incorrect.
The iceberg.
About a third above the water and about 2/3 below.
Yeah.
And then when you stated it, you said, let's get rid of half of the iceberg and you took away the big idea, which is, again, scientifically incorrect.
Thank you. You're exactly right, and I'll fix that for the next presentation.
Chris, on the website, you had mentioned all of the big ideas for the different courses within the college, different courses are there for the AD, and I'm having trouble finding them. So, like, I'm on the biology site, just so maybe we might want to reference our discipline.
I'll come around.
Okay, all right, great, thanks.
So, so take about 15 minutes to begin to do this task, and then if you have questions, let one of us know. We'll try to come over and point you in the right direction.
I think we some of us have forgotten their instructions. Actually, I remember that you gave them.
Right. Okay. So let me say the instructions one more time. No. And I also said I would put up the science practices. Which actually, I think the science practice, let me reiterate the instructions for just a second, but rather than putting up the science practices, I think actually the iceberg, which if you can get over the fact that it's scientifically incorrect to start, has some useful information there. So I'll put that up to start, because what you need to do in the beginning is to think of the content of your own courses and try to design or come up with 4, certainly no more than 5, big ideas that serve as the organizational principles of your course. And then take one of those and begin to think about what are the enduring understandings? What is the durable knowledge? What do you want a student to know 50 years after leaving your course?